Welcome to the London Haskell Users Group. Bill came up with the idea of putting it on Meetup a few months ago. I volunteered to help him, and after a little disorganization, we've made it here to our first talk. Why do monads matter? So I'm not an expert, and when I saw the people who signed up, I was beginning to get worried I'd got you all here under false pretenses, okay? I've dabbled in Haskell for a long time. I'd classify myself as I'm an amateur, in the old sense of the word, that I do it for the love of it. Okay. But I'd just like you to bear this thought in mind while you're listening to me tonight, which is, whether you're a beginner or an expert, I am proof, assuming this doesn't go horribly wrong, that you can get up here and give a talk, okay? Because we basically, if we want this, the user group was going a few years ago, it kind of petered out. If we want it to keep going, and there should be enough demand here in London, you're all proof that we can get it going. So, okay, so why do monads matter? Now, if you've got your Google page out, you've typed in why do monads matter, you press search, you'd have seen this top link here, okay? It's a blog post, and this talk is a shameless steal of that blog post. Don't worry, I got permission. I asked Chris, I said, do you mind? It's a really good blog post. Do you mind if I use it? When I was thinking, oh crap, what do I talk about? So, yeah, Chris asked the question, why do blogs matter? Why do monads matter? And I recommend it as a read. If you haven't already read it already, if you have read it, I hope I do it justice. I'm going to do some live coding. So, if you do know all this stuff already, just sit back, enjoy the spectacle. There's real potential for this being car crash TV. So, GUI theory. Is it something, as practical software developers, that we should be worrying about? Is it a match made in heaven, or is it just abstraction distraction? Okay. Now, you may have tried watching the Channel 9 videos. You may have tried reading the books. Trust me, I was going to take a photo of all the books I've bought. None of them have sunk in for me. Okay. So, quick quiz for you. Do programmers use functions? Okay. Hands up for no. Hands up for yes. Oh, good. I didn't have to ask too many about the undecided there. Okay. Of course they do. It's a bit like asking, do carpenters use nails? But it's a bit more complicated. You ask a mathematician, what's a function? And he'll give you a fairly simple definition. It's a mapping from the domain to the range, from one value to another value. Okay, it's simple. If it's a real thing, then he can plot it as a graph. But you ask a computer programmer about a function, and he's going to say, oh yeah, you've got printf, and you've got that one that generates the random numbers that I didn't have a chance to look up, and the one that tells you what day of the week it is, and all these things that we call functions, but they're not really functions like a mathematician would say it. Okay? So, are they functions or something different? Well, they have parameters, so they have a domain. And they have return values, so they have a range. And we can compose them. And composing functions is a really important thing. Okay? So, composition is where you take two functions, and you put them together and you make a new function. Okay? But the range and the domain must match. If we have A and B, so we've got a function going from A to B, we have another function that goes from B to C. As long as these two here match, we're good to go. We can build a single function that goes from A to C. Okay, so that's composition. Okay. So, the executive summary, again, shamelessly stolen from the blog. When computer programmers talk about functions, they mean something like functions, but not quite the same as a mathematician would mean. Okay? So they do have inputs, they do have outputs, and they have composition. Okay? So, quick detour here into category theory. Okay? Don't worry, this isn't going to get too heavy, because I already don't understand everything that's in the talk. So, but this is the definition as I've seen it in the books. Okay? Our copy and paste does a great job here. So you have some objects, you have some arrows, and you should think of those as functions. was thinking there's little lines going from one to the other, but and each arrow has a domain and a range, and we have some identity arrows, which means kind of like, we just loop around in the same place, and we can compose them as long as our domains and range match up. Yeah, and the identity doesn't break anything. And we also have associativity, okay? So let's try and do this in a diagram. So we have some objects here. I've drawn them as nice little ovals. There's space inside them because they're sets, or something like sets. And we have some arrows, okay? And we have this arrow here. This arrow here has the domain and range. I haven't labeled them all, but those two are there, okay? We have some identities. And if we compose those two arrows together, we get this arrow here, okay? To show you associativity, I need to add a few more things, but if those two arrows are composed together to give that one, and those two arrows composed together to give that one, then basically the associativity says that those two on the outside must be the same as those two, okay? And that's it. That's all a category gives you, okay? But if it is a category, all of that lot is true. So Chris goes on to give some examples here, and this is where I'm going to defer to him because he knows more about this than I do. So there are lots of examples there, nice mathematical things that I'm not going to actually read them out because I wouldn't do them justice, and you're going to probably then want to ask me questions about them, and I'm going to go cough, splutter, cough, splutter. But we're all programmers. We have day-to-day jobs. We don't deal in high and mighty mathematical ideas. We deal in ugly problems. And along come the four horsemen of the cat-apocalypse, as Chris christens them. We have failure. We have dependence. We have non-determinism. And we have destruction. So, what are the problems that these horsemen present to us? Well, those functions might fail. We might get an answer, and we might get an error. Oh dear, not good. And dependence. Now, I'd get my phone out, but I've put it away. But, they're not self-contained things, these functions. They're messy, yeah? Our programs all have data that we want from over here, and we want it down here, and we want to kind of have it all over the place. And we don't really want to use global variables because, well, somebody a long time ago told us, no, you shouldn't do those things, okay? But lots of our programs depend on this common knowledge. And then we have uncertainty, okay, non-determinism. So normally, a function associates each input to one output. But sometimes, we have problems where we have a number of possible outputs. So and these things don't turn up much in general purpose languages, but they turn up a lot in special purposes languages. So parsing and search, slides too, verification and query. So finally, the one that everybody kind of bumps into with monads is destruction, or changing the world, okay? We want to be able to see what's going on inside that computer. A computer with no observable effects is just, it's warming the room nicely. So they have to have effects. And yeah, Chris got there and said it first. So, and the problem is though, these effects, the order matters. We can't just rejig things around and expect them to stay exactly as we expect them to. It might work, it might not do. So we have to have some way of controlling these issues. So, we started off with functions and the way that we were using them. And it looks rather like we're in trouble here. The lovely word of mathematics has been left behind. Okay? But don't fear, we haven't lost out. Because we can still do something. Okay? We can write functions that deal with failure, but they have to be a bit special. Okay? So effectively, we take our function that produces the intended result, and then we say, okay, fine, we might get some errors back from it. And we have something that describes the whole of this. So if we had our function that was going to return something from A, we can define this error of A, which includes both the successes and the failures. Okay? So that's the first one. And dependence, well, we can pull a similar trick here. So we want to take our pure functions and we want to somehow get the configuration settings in there. And we don't want to have to do all this plumbing ourselves. So wouldn't it be nice if behind the scenes there was a way of passing in the parameters to our functions, every time we want to do it. And if we define ourselves, this pref that is basically it's our functions that return A's, but with this extra input into them. Uncertainty, well, this one's the easy one for the mathematicians to do. They talk about power sets all the time. So this is where you don't just say, okay, fine, we're going to get a value. We're going to get a set of them, or some set of the whole bag. Okay. So basically, we turn our ordinary functions from A to B into functions from A to the power set of B. And destruction. Okay, a little bit more tricky, but hopefully once you've seen the code, this will make a bit more sense. What we're going to do here is we're going to separate the time the destructive effects happen from the creation of them. And our pure functions will create these instruction lists. And I'm using that very liberally because it's there isn't an easy way of talking about this without kind of starting to get very loose with your language. But effectively, rather than getting an A, we get some instructions for obtaining an A. But what about composition? We've lost it. Okay? Because we've got these functions that go from A to the error of B, and then from B to error of C, and that's not going to match up. We have a problem here in the middle. They don't match up. So, oh dear. What do we do at this point? Well, hold your horses. Henrik Kleisli to the rescue. Okay. Some mathematician, one of these ones with the small glasses, from Switzerland as far as I can tell from Wikipedia. He spent some time studying these special functions, and he found that as long as there are certain rules, you can compose them in a special way. And these special functions, we call them Kleisli arrows after him. And we do effectively Kleisli composition with them, and we have a new kind of category which we're going to call a Kleisli category. So, A, B, and C. These are three ordinary sets. So if you just imagine, say, that's strings, this is integers, and this is a Boolean. So we might say, okay, passing in some string, we'll check how long it is, and then we will test whether it's, I don't know, less than 10 characters. So that's the piece of code to have in mind here. Now, error A, error B, and error C are the results. This is getting back a string or a failure. This is getting back an integer or a failure, and this is getting back a Boolean or a failure. Okay? I'm just going to draw them down here so that they line up. We kind of see, yeah, A's, B's, and C's. So these are from A to B, and these are our Kleisli arrows. So you can see here this is coming down from A to the error of B, and down from B to the error of C. Now we don't really need error A. I just drew it in there to make nice and neat things. So I'm going to just rub it out at this point. Now, those top two arrows are normal functions, and we can compose them as we would do, and we can replace those two by a single function from A to C. But what can we do with these ones? As long as they follow the rules, we can position with them. I don't know if that's a proper word, but that's the word I'm going to use tonight. And we can basically replace those two with a single arrow that goes from A down to error C. So, what do we need? Okay. The objects, and this is where the objects. Now they're basically the same as we had before. They're just sets of things. The arrows are these Kleisli arrows that we're talking about, but I have kind of haven't given much of a definition of them yet. But what are we going to do about identities and composition? Well, let's go through. Okay, let's take error as an example here. We've got a function that goes from A to error of B and B to error of C. We want to compose them together. Well, that's basically saying we'll do something, and if it's okay, we'll carry on and do the second thing. Okay, so how do we compose them? Well, if the first function reports an error, I mean, this isn't the only way to compose them. You could think of other ways of doing it, but this is the way I'm going to look at tonight. If the first error gives a function, then stop and don't bother doing the second function. But if the first error is okay, take the result of that first error, and because we're composing them here, we feed that into the second function. Okay? So basically, the definition down the bottom here, this is saying, kind of like, we just got what came back from G. And if it wasn't an error, then we've got what came back from G, and we're feeding that into F. And the identities, well, they don't do anything. So we literally can have what amounts to the identity function. We just say, we're never going to get an error out of identities. Can we do the same with dependents? Well, yes, I think we can. Sorry, my slides are wrong title. Let's see what the next one is. Yeah, nice. Okay, fine. I got the titles mixed up. So non-determinism. Is it non-determinism? No, this is. Oh, sorry. I know. I'm getting. It's not my slides. So preferences. If you're composing two functions, what's the obvious thing to do? Well, let's use the same configuration for both of them. So we can, if we're composing the two together, we'll get some configuration in. We feed that to both of them, and that should do the trick. And the Kleisli, well, it gets the configuration, and it doesn't have anything to do with it, so it can just throw it away. For non-determinism, this is about having sets of possibilities. So if we've got two possibilities out of the first function, and then for each of those two possibilities we'd get 3 more possibilities out of the second function, then in theory we should be getting 6 possibilities. So effectively, second function to each element that's come out of that, the results of the first one. And with the destructive effects, well, effectively we just need to make sure that the order is kept correct here. So we do them in a stepwise manner. We do the first one, and then we look up what we're going to do next in the results of the first one, and step on to the second one. So, and now I start to forget what my slides say. Right, okay, I think at this point, I'm going to cut to doing some coding. Here goes the high-risk strategy. So if we work through each of these examples, and I'm hopefully, with me typing the code, you should be able to see it. And if people get really bored, start heckling from the back. Okay, so I was looking for something that could fail. So I thought division. Division by 0, that's one thing that can fail. And I've got this function, DivBy, which basically is going to, just let me get in the right directory here, and GHCI is basically going to do division for me. So I'm going to pass in a parameter and thing. So div is the integer division, and that basically does, so div82 would give you fallback. Can everybody see the font? Do I need to make it any bigger? Is it good at the back? Yeah, okay. Starting to glaze over. Okay, so DivBy takes a parameter. Code here is saying divide by, says we want to divide by 5. So effectively, we should take the value in, divide it by 5, and then divide it by 2, or divide it by 7, and then divide it by 3, or divide it by 11, and divide it by 5. End of the parameters. Work, and that, and I'm going to be good. And put a signature in here. I can't type because you're all watching. Sorry, this is going to get painful, I'm sure. Yep, it's going to get painful. Okay, so if I go around, load this up. Hey, it worked. Okay, and there we get the answers we expected. Phew. One demo down, off we go. So let's introduce an error. Let's imagine that we do a divide by 0 here. Okay. Anybody know what, if I type main, actually, if I type main in, I'll get exactly the same as before. If I reload it and type in main, any guesses what we're going to get? Yes, good. That person's written that code before. Now, the key point to note here, I don't get the answer 42. Okay? I've lost it. It's kind of done that one, and then this is the one that goes bang, and then I've lost this guy, and that's not so clever. So what I'd really like to do here is be able to get this to work. So the problem is that Haskell, when it hits an error it doesn't know how to deal with, basically goes bang, that's it, stop. I was going to look up the definition of error, but I didn't get around to it, so I'm just going to have to do it off the top of my head. But effectively, it just stops the execution of your program. That's it, terminate. So that's not so clever. So we're going to have to work out some means of dealing with this. So if we use the same trick that we were talking about before, and say we're going to have this error A, which is the values from A, but it's also got, and I'm just going to have one error. I could have more, but that would make my typing even slower. So this is an algebraic data type, 2 options, and I've put this deriving show in so that I can print out copies of it. And I want to start using this in the program. So first thing we're going to do is say, okay, fine, let's take DivBy and say, if I get a 0 as my parameter, then we're going to basically say that's an error. And otherwise, it's an OK value, and we'll do it. And if I try and compile that, it's going to say, oh dear, I don't like the types. So at that point, I go back and do what I normally do, is just randomly start changing the types until it compiles. Because the type checker understands how these things work, and I don't really. And I still have a problem. Yes, OK. So it's got past compiling this first piece of code. So this is all good, but it's now complaining about this. And in fact, I know, because I prepared this one earlier, it's complaining about this composition here. We've run into this problem which we can't compose these functions anymore, because this is returning an error integer, not an integer. Whereas DivBy, it wants an integer in. So we're going to have to do something about this. And little did you think that I'd finished with this one. I'm going to have to do some more typing. So the type of composition is basically, and I'm just doing this as a comment so I can, it's back to front. I mean, you'd expect it to be A to B and then B to C, and then and that gives you a thing. But because F is the first parameter, then you've got the B to C bit, and then you've got another function. This is the G bit that is A to B. And finally, you get back the result, which is the A to C. And this A here is the X here. So if I take this and I basically turn it into these Kleisli arrows, then basically we have error on each of these. Okay, so this is the function we want to write. Okay, and at this point, I do my normal trick of going undefined, and that just tells the type checker just think of whatever you want it to be that will make your life easier, and life will be fine until I actually try and run this. So, and I've replaced the normal composition by this compose error, and I've used backticks here. Backticks take a normal function and turn it into an operator. So I can write it infix. And so if I save that, reload, hey, it's compiled. I'm impressed, even if you aren't. Right, so, and problem is now if I type main, it says undefined. Whoops. So we have to come around and we actually have to write some code here. Now, I need to put some parameters in here. So f and g are my two functions, and I'm going to write my x in here because it makes it easier for me to know what I'm doing. I could write it point free, but I'm not hard enough for that. So the first thing we do here, delete that for a second, is g is the first function we apply. So we've got this x. That's the first, that's the value we get given, and we're going to apply g to it. And then I want to take the result of that apart and pattern match it. And case is the way that you can do that in line. And nobody's shouting at me that I forgot my of. So what am I going to get back here? Well, there are two possible values here. There's OK and there's error. That's what our algebraic data type said. So I've got an OK value here, and I've got an error value here. Now, there'll be a value inside the OK. And anybody care to guess what we're going to do with that value? What are we going to do with y? Go on. F of y, yes. Prizes for everybody at this point. And if we remember back to the slide I had, what happened if I had an error? Exactly. See, you could write this code. And at that point, I think I'm good to go. Well, hey, it compiles still, and it runs, and here we go. Go on, round of applause. You know you want to. Yeah. Thank you. We didn't write here is these identity functions. We didn't really need it for the example I gave, and that's probably because my example was so bad. But I'm going to write it anyway, just to show you that it's not too scary. So what we said with this one is that, well, we're never going to get an error from this. We've been given an x, and we can just basically wrap it up and return it back as an OKX. And that is us done. Just check it loads, and that's great. So that's our first example. So failure has been beaten into submission. So dependence. I thought by this stage you'd probably be getting bored of me typing, so I've kind of left this one up. This is, think of a pretty printer. Okay, so I've written this repeat string, which takes takes an integer in and a string, and basically appends. What does it do? It repeats that string that many times by recursion. So if I load up depend. Oh, what did I say that as? No, preferences. Teach me for changing my routine halfway through. Oh dear, and I'll get errors. Not in scope. That's because they're supposed to be hard-coded values at this point. Try that. Hey, right, okay. So repeat string is just basically takes an integer, so 5 and ABC, and repeats it 5 times. So nothing complicated there. And then left puts 3 copies of the angle brackets on the left of the string, and right puts it. So, and I just basically, I compose those two together to get a lefty-righty thing. And in fact, I could just change this here to say, just to make it a bit more interesting, so I'll have 2 copies of the right thing. So if we reload, run it, you can see here that we've got extra ones on the right and only 3 on the left. It would be nice if we could take these 3s here and we could lift them out. I can have a global variable. So I can say, okay, fine, here's my integer. I'm going to say it's equal to 4. Actually, I'll say it's equal to 3. Do a like-for-like replacement and put my integer in here. Okay, and that'll work, but it's not particularly pretty. And I might want to have different bits of configuration passing around, and tell you the truth, I'll probably, by the time I've got 26 bits of configuration, I'll have run out of variable names. So, turns over the page to see where he's up to. Yep. But being good Haskell programmers, I will have separated that. So I'll have done my reading in my IO monad, and then I'll have come and passed it around. So we want to have a type for the configuration, and I've kept it simple. So I'm just going to use a type synonym here to say that the config is an integer. And basically, does anybody remember how we did this? What were we doing with the preferences? The preferences, if I spell it correctly, the preferences for A were a function from the configuration settings to those A values. And you write it exactly as you'd expect to write it. I can't type it, but so this is basically saying that when I call this thing a preference, I'm basically saying I have a function from a configuration, so I pass in the configuration to it and I will get back an A. And at this point, we should be able to go through and say, okay, so do the same thing as before, say that this is, put them into make them Kleisli arrows, and I'm going to write these as, I'm going to put the function in here. So this is the syntax for an anonymous function. So this here is all a function that takes an I and does something with it. Okay, and then I can do the same here. And then I can try and work out what else I need to do to make it work. Is that enough? I guess I'm going to actually, yes, all right, I'm going to need to pass in, so I'm going to need to pass in my configuration here. Get rid of that. And at this point, I'm going to try and compile it, and it's going to complain again. It's the composition. So off we go again to do the hard work. Here, just double check what I did before. Right, okay, fine. I'm going to cheat this time. I'm going to copy the start of my definition off here. You are getting bored, aren't you? I'm going to browbeat you into submission. You will understand this, and if you don't, you'll have given up by the end of it. Because if that idiot can witter on for that amount of time. Right, so that's the signature of the thing that we want to write. Now, anybody remember what we were going to do with the configuration? We were going to get in a configuration, and what were we going to do with it? We're going to pass it to both functions. It's not a lively audience tonight. Okay, so this is our configuration coming in. And then we're going to get the value back out from calling the first function. Oh, almost made a mistake there. So that's the first function. And we're going to pass in the configuration. So if you remember that if you look at this here, the order in which we pass them is, this is a function that takes a string, and then it takes the configuration setting, and then it finally returns you back a string. So the configuration setting is kind of here in the middle. Okay? And that's why with G, we pass it the X, and then we pass it the configuration setting. And then, as before, we'll take that value there, and we'll take the output of that, and we're going to pass in the same thing here. So this C here, I really shouldn't, should use a different letter. Oh dear. Banging my keyboard too hard. Hard disk protection is complaining at me. So, and just even though I don't need it, I'm going to write the identity here. And that takes an A and puts us into the preference thing. And if we remember rightly, this was basically is a function that took the configuration settings and it ignored them. Now, in Haskell, you have the way of saying this is a parameter I don't care about, of calling it an underscore, and so basically that is the throw away the configuration settings and just give me back the X that you gave me. So, try and load it, and everybody who is paying attention will have spotted the fact that I didn't actually bother to use my lovely new code. Okay, try again. Oh, hey, there we go. That's the second one done. So that's two of the problems where we've said we're going to move to using Kleisli arrows, and we're going to pay the price of defining our composition and identity, and we're going to define the composition in the way that's the right meaning for the problem at hand and the solution we want. So, uncertainty. Okay, now, anybody who came to Haskell Hoodlums last week will remember the blackjack scoring problem, and I'm going to take that as the basis for what I'm doing here. And I'm going to have to type a bit quicker because there's more code in this one. So blackjack, or 21 as it's sometimes called, you're dealt a number of cards, 2 or more, and the aim is to score as high a number as you can without going over 21. There are aces. The number cards are scored as their value, and the pitch cards are scored as 10. So the first thing we're going to do is write a function that values each card. So it takes a card and it returns you back. I really should have just cut and paste all this code, but it wouldn't have been half as exciting. So the value of the card for the ace is 1. For a number, which I'm putting in brackets so that I don't kind of get it all split up, is just the number on that one, and I'm ignoring if somebody's passing me in, the number 75 card, which my son would be writing all the extra dots on the card, and my pitch card is there. So at that point, if I just load this up, I should be able to do value card ace, that's a 1, and a picture card, it's a 10. And anybody have any preferences of what number? 7. There we go. My lucky card. Right, and now we want to value hands. I'm just going to represent a hand as a list of cards, something simple. And we're going to get back an integer from this. So this is the value of the card. Okay. Now, the problem in terms of non-determinism is going to come in with this line here later, because when you're playing blackjack, you get a choice of whether your aces are worth 1 or 11. But for the moment, I'm going to ignore that. In fact, I'm going to cheat here, and I'm going to find some code I prepared earlier, because you don't want to watch me type this, because and basically what I want you to do is I'm just going to let's just for a moment just say I value my hands all at 42, and there we go. So that code's clearly working. There are no problems there at all. But if we wanted to write it properly, well, an empty hand, I'll say that's worth nothing. And if we have a list of cards, well, let's split off the first card in there, and we can just use value card to give us the value of that, and then we can add together with the value of the rest of the hand. There we go. And assuming I haven't made any mistakes, there we go. So if we just look, get the two running at the side by side, so we can actually see what we're valuing here. So the first one is an empty hand. Second one is ace 2 3. That's ace ace 2. That's 3 aces. 2 pitch cards, ace and a pitch card, ace and 2 pitch cards, and ace and 3 pitch cards. Now you might make an argument that 31 isn't the a real legal value, but until I can think of a better answer for that one, I'm sticking with that. Now, what happens if we say, okay, we want to be able to have this values? Now, we can represent power sets by our list of answers. Sorry, what we'll have here is we won't have a 1. We're going to say 1 or 11, okay? And I'll just introduce P for the power set as a type synonym for the list, and that means that we can kind of go through and say, okay, fine, value card will give us back a non-deterministic integer, and value hand will give us back a non-deterministic integer. And then basically, yeah, at that point, I just kind of look at my code and think, what on earth am I going to do next? I'm going to try and run it. And it's all going to crash and burn. Now, which one? Where?
Line 9.
Yeah, sorry, you're right. I'm jumping ahead of myself. So we need to put those into brackets, and it's still not going to work because I'll tell you, it's this addition here. So I'm going to cheat like I normally do. I'm going to comment out that stuff. If I delete all my code, then it all works. And then I'm going to kind of say, okay, putting the problem to one side, I'm going to go and write the compose function because that's what I know I'm going to have to do at some point. Because we've turned these things into Kleisli arrows, and we haven't dealt with how they compose together. So we want this function here, and I am going to, just to keep things moving along, I'm going to gratuitously cheat here, and I'm going to use a list comprehension. So basically what we said was we're going to take all the answers we got out of applying G to X, and then we're going to apply F to each of those. So if I pull out when I apply G to X, I'm going to get back a list. And if I pull a value out of that piecewise and call that Y, and then I basically say, okay, fine, let's apply F to Y, and I'll get back a list, then I can basically pull my Zs out of that. And if I just, there we go, press the right key. And then I need to just fix this one up here. So, yeah, I do too. You lot are paying attention still. I was expecting you to have fallen asleep by now. So, that's not right. So basically, for the identity, we'll just return the one element we were given as a list, which effectively turns it into takes an A and turns it into a PA. Now, let's see if that compiles. That compiles. So, as Haskell folklore says, it is by definition correct at this point, and there is just no way that I can have made a mistake. And I tell you, if I spent as long showing you how I wrote this code as I did on Saturday evening when I was really writing it, we'd be still here tomorrow. So I'm going to just kind of cut to the chase. And after messing around and trying various ideas, I realized what I really wanted is I wanted a non-deterministic add here. Okay? I want a way of adding together two integers non-deterministically. So basically, and I'm taking a power set of integers, a non-deterministic, yeah, I should have called it a different name, but trust me for like starting off the thing. So these are two lists of integers, and I want to add them together. And again, I'm going to cheat for the moment, and I'm just going to use a list comprehension because it makes it nice and clear what we're doing, and follow the same style of code that we did with the same typing mistakes that we had for the composition. So X is pulled out of the X's, and Y is pulled out of the Y's. And then I'm going to add them together, and that's your value. And if I just check, I can still compile. So if we go add P here of 1, 2, and 5, 10. So we get all the combinations of adding 1 and 2 onto 5 and 10. So there's 5 plus 1, 10 plus 1, 5 plus 2, and 10 plus 2. So that code looks like it's working. So maybe we can put back in some of the code that we commented out while we're breaking things. So let's put this one back in first. That's not the right way. So this is a power set of integers, so I need to put brackets around that one, as everybody said. And then the value card returns a power set of integers, a non-deterministic integer, and value hand will also return that, and this guy adds them together. So let's see if that compiles. As you can see, I never do much without actually checking the compiler. Still gives me a tick of approval. And let's put that back in. So does anybody want to run this? There we go. So the empty hand still evaluates to 0, and the hand which is ace 2 3, well, depending on whether the ace was a 1 or an 11, we get either 6 or 16. This had the 2 aces in it, this had 3 aces. Now there are some duplicates in here. I haven't worried about getting rid of them. So my list representation is a bit of a kind of sloppy one, but it'll do. It'll do. You know, I think, oh crap, where's the code? The next piece of code I was going to write. Because what we really want to do is we want to find out the best value for this hand. So I'm going to take this code here, and I'm going to say, well, the rules of blackjack say you want the highest hand you can have without going over 21, so not going bust. I'm going to turn this into a helper function. And we want to get just one integer back. So we'll change the type signature. Turn this into a helper function. And I'm sure people are going to start sitting in the back thinking, you could have written that code much better. And that's almost certainly true. I'd argue I'm trying to make it clear. You'd probably argue I don't know what I'm doing. But so our list of cards comes in, and we first of all want to pull out all the possible hand values for it. So we call HV on our list of cards, and then we basically say, okay, let's ignore any values that are over 21 and just give ourselves a list of the non-bust hands. So we can filter down that list, and we get so we filter down our HVS list, which is all the hands, and then we basically say if not, so if and yeah, and then we'll basically get the maximum non-bust hand. Okay, reload. Hey, it still works. And we were doing all right until this last guy here. And I'm kind of going off topic here, but I just wanted to make my code complete. Basically, if we remember back, this was the hand that had the value of 31. So we need to check if this list here, this non-bust list, is empty or not. And if it is empty, so null is the test for it being empty. And we want to say if it's not empty, I guess I could have written it the other way around, but if it's not empty, then we get the maximum value out of the non-bust thing. But if it is empty, then we basically have the minimum of that HVS list. Okay, so the smallest one, and we're assuming that every hand has at least one value here. So is that going to work? Looks it compiles, so yes, it's going to work. So that's basically non-deterministically valuing blackjack hands. So you can see here that we've got hands with 2 or 3 aces. 16 was ace 2 3. That's the best version of that one, so that's valuing it at 11, whereas this 21 here is the first one is an ace plus a picture card, and the second one is an ace plus 2 picture cards. So you can see how it's kind of depending on which one we wanted. And this code, it's not very pretty, but it's pretty clear what it's doing. You know, it's you could wave that in front of a business analyst and say, "There you go, mate." go and lose your shirt in Las Vegas. So, destruction. I'm going to go a bit faster here because you're all going to be getting bored, and also trying to explain this stuff in a way that makes sense is going to take me too long. I know, heckle from the back. But I mean, it's kind of like, basically, in fact, I'm going to cheat again, and I'm going to find the code I prepared earlier.
That was a quick one.
Yeah. Okay, just turn it. Actually, no, let's not do that. Let's type it in, actually, because it's way too far ahead. So I'm going to define a little I/O language here. So I've got wait for input, which basically takes a string, puts a message on the screen, and then basically waits for you to type something in, and that's it. And basically, just cheating again here, I'm going to write the equivalent Haskell, and so that you all get the idea of what we're trying to aim at, or you kind of think, I have no idea what the guy's talking about anymore. So that's a wait for input, and we have my reverse output. I tell you, think of examples. It just, you kind of think they're all trivial, they're all silly, and you think that'll have to do. So this one takes a string and basically prints out the reverse of that string. So that's those two functions defined, and we want to we're aiming for the following effect. So using the Haskell do notation, which I am not going to explain at this point, so you either know what it means or you just have to kind of assume it means what it looks like it should do. So we're going to do this one first, and we're going to take the output of that and call it S, and then we're going to take whatever the user typed in, which is called S, and we're going to print it out. And at that point, I should have some working code. There we go. Right. So that's basically the kind of working example. Now, because we're doing this with function composition, because that's the only tool we put in our toolbox, and so everything has to look like composition in the end. We really want to write the code something like this. So we're composing this function with this one, and that's off the way we go. So now we need some way of representing the I/O, and I always kind of think of it as I/O actions. And so basically, I'm going to define a little data type here that is, we have a couple of tags in our algebraic data type, or constructors, as we should call them. So output, this is the one that basically puts things on the screen, and wait is the one that gets things from the user. So we need to give output a string to put on the screen, and then the other thing we need to know is what to do next. So this is where we just say, okay, well, we'll just say there's another action embedded in here, and that's what we're going to do next. Wait is a bit more tricky. The thing that's running our I/O actions is going to get this string from the user, and then it's going to say, and what do I do next with it? Now, if it just jumps to the next I/O action, then where's the string gone? So what you want to have here is, I think, I'm going to stick my neck out and say it is a continuation. Big long word, computer science, didn't ever study at university. And basically, it's a function that says this is what I do next. So effectively, the string that the user puts in is going to be passed to this continuation, and it is going to give us back an action to execute next. So at that point, I hope I have running code. I do. So we're still now. This is all well and good. So we have our list of actions, but we need some way of doing something with them. And again, I'm going to cheat, and I'm not really going to kind of give you the whole of the train of thought here, because otherwise we'd kind of go down an awful lot of dead ends. And trust me, it wasn't pretty. So we're basically going to have what amounts to a little interpreter for these actions. So it takes, we've got our output, that's our string, that's our next action, and then we're going to do something with it. And we're going to have a similar one here for weights, and this is our continuation function. So, and I don't know what to think, but I'm already getting uncomfortable that it's been too long since I've been blessed by the type checker. So we've got to somehow take the action that we're expected to do. So, and this is all where it gets horribly circular, that I'm going to have my interpreter for my I/O actions, and I'm going to implement it using the Haskell I/O monad. Just ignore that. Imagine I'm writing your favorite programming language, Python, Ruby, C#, assembler, whatever, to write this this little interpreter. So the first thing we're going to do is print out that string, because that's basically the first action shit. And then we're going to continue by saying, okay, well, let's just run the next action. And with the waiting for the input, well, we need to get some text from the user, and the function to do that is getLine, and the notation to put that into a variable. Actually, no. To give it a name, I shouldn't use the term variable, because they're not variables. So it's now the string the user you gave is now called S, and we can basically say, okay, fine, let's run the next action. Now, we don't have our n here, so where do we get the next action? Well, this f is a function from string to IO action, so I'm just going to pass it the only string I have lying around and hope that works. Oh, it still compiles. It must work. Yeah, no, I'm trying to find my test code now. Actually, I should be able to run IO. Let's do output. Foo. Yes. Well, I'll put undefined, because that's what I always put in these cases. Oh, we got our foo out. That's good. But then we had. So I have a problem here. I don't know what to put here, and it's like, yeah, I'm a bit stuck, because well, it's either output or wait. Now, those people that know this stuff will know that I'm missing something. So I'm just going to park this problem for a moment, and I'm going to say, well, let's just try and write the composition and the identity functions, because it kind of works. It compiles. So if we go and take our type signature for composition and these, and I'll just undefined, and then I change these to IO action, and then go through. Yes. You clearly need to kind of have a means of sort of just barracking me to go faster. It would probably make my typing worse, but okay, let's check. Well, that still compiles, but we haven't got implementations of these. So, where are we? Okay. So if we try and write this one, so let's start with the case statement like we had before. So we apply G to X, and then we see what we get back, and we're either going to get an output and SN And so just leave that for the moment, or we're going to get a wait. So what are we going to do when we're composing these things? Well, G is the first one, and if G is an output, well, I think we ought to basically output the string. But we've got to put F somewhere. So F is kind of the next one, the next thing we want to do, but G already had this next action in it. So basically, we're going to stuff the F inside and hope that it all works out. If you want to understand this stuff properly, by the way, just work through the examples later. You will eventually, after a bit of banging your head against the wall, the penny will drop. And so we're going to compose our F with the remaining action. And tell you the truth, I don't know why I put this code like this. Somebody might be able to tell me whether there's a better way of writing, but this was the way I got it to work. So this is our continuation, and we're basically going to throw away the parameters to it. That doesn't look right, but anyway, it works. And okay, waiting. Well, that basically will wait, and then we will take the string that we came back from our wait, and we will basically pass it in to F. It's all right. Helps if you don't have two Fs. That's why I was getting confused there. I was about to write FF. F with the next action to take, because that's what this wraps up, this continuation function, and the string that we've just got there. Hopefully that compiles, yes. So we've got those. Let's try and write the identity function. So we want something that takes an A and returns an IO action of A and doesn't do anything. Now, is that an output? No. Is it a wait? No. Oh dear. I've missed something. Now, I'm going to call it return. And it's going to be boring. It's just going to be a return A. I'm calling it return because that's what it's normally called. And that means that I can basically say, okay, when I just want to wrap something in and make it an IO action, but all it does is say, here's back what you gave me, then that's return. So at this point, we can go back up and we can say, maybe we can write this. Maybe we can write return unit. I'm liberal with my brackets. And I forgot to reload. And now it complains. Yeah, it should be an X. Okay. And I haven't got any exhaustive patterns. That's because, yeah, we haven't got our run here. So we better add our cases. So return X equals, what does this do? Doesn't do much. It gets circular, but and if we have a return here, well, basically, we've got the value it's wrapping. Well, we'll just apply F to that, because that's basically the only thing that we can do at this point. Because we've used our G, F's the only thing left, and this is where we really hope that the types line up. And they do still. And if I try and run that, well, hey, I get a foo. So I'm not going to subject you to kind of writing that. Now, at that point, 7:45, I can go back to the slides, or we can just push on a bit with the code. Does anybody want me to go back to the slides or push on with the or go back to the code? Code? Code, yes, that's the answer I wanted. He's a stooge at the back there. So at this point, I kind of thought, right, let's try and write some of these. Well, actually, let me just stop a second. At this point, these are all monads. Okay? We started off with our Kleisli arrows. We defined our composition. We defined our identity. And I've got a slide in a moment, but basically, you're home free. You've got a monad, slam dunk. Don't worry about proving anything. So I thought, okay, let's try and write some of the functions you find. And so there's this join function, and it has the type that basically it flattens out one of these structures. So it'll take a power set of power sets, and it'll give you back a power set. SIGFPE had a blog which I didn't include in the thing, but I quite liked his quote, which is, twice as fancy is still fancy. So we'll take in our list of x's, our list of x's, and at this point, I kind of go, actually, let me just back up a second. Anybody who is uncomfortable about this, I'm going to kind of say, okay, fine, fair point. Let's redefine this without using list comprehensions. So I sat down to try and write this code, and again, it took me a while. But I started off saying, okay, fine, we'll apply g to x, and then we can't apply f to it quite. So I said, I want a helper function here. And I'll define my helper function to say, okay, fine, if I have an empty list, then I get nothing back. And if I have a list with a y at the front, I can just apply my f to my y, because they should be the right types, because this is just one of them now. And then I can concatenate that with the rest of with h applied to the rest of the list. And it helps if you load the right code. That still works. I haven't broken it. So my little cheat of using a list comprehension, I've replaced it with this, which not quite as clear maybe, but I'd kind of argue it's more honest. So let's go back to trying to write this piece of code here. And you'll see. Yeah, no, there almost certainly is, but yeah, don't ask me what it is. Go on then. What is it? Okay. Yes, in fact, I did realize that you could do that. So yes, we can in fact change that to concat app. But there we go. Comment that out. Yeah. Good. Right. Okay. Rather destroys the point I'm about to make, but that's that. Don't worry. We'll so I sat here working out, thinking, crap, I must be able to write this. I really must be able to write this. So I kind of thought, well, I'll pull that same trick of I'll have a helper function. So I'll just kind of I'll pass h to this is my thing. Now I know you're kind of thinking that what on earth is he doing? But that's just kind of like what I was doing. You know, it was getting late. So I kind of said, well, okay, fine, what will h do? Well, if it's an empty list, then I want the empty list back. And if it's I've got a list with a thing, and I was just kind of just following the types and just writing what code I could write, then okay, well, I'll have the y and I'll append to that h of the YS's. And I kind of at this point thought, and this is where it kind of like you rather spoiled my point with changing the concat map. I thought this, if I squint hard, looks kind of like the code we had here. But it just, well, I've my G there I'll just have to put an identity in. And my f here, well, if I put an identity in here, then, yeah, that should do it. And I thought, well, does that mean that I can write this as this? Because that's what the code's telling me. So let's put that back in. I said, OK, let's try that. And let's do a join p of. So this is the one that kind of squidges together our lists of lists. And it flattens it out. So yeah, so compose p is good enough to write join p. That's not too bad. And bind is another one that comes up in your monadic programming. And this is the one that basically takes a PA and a function that goes, one of those Kleisli arrows that goes from an A to a PB and gives us back a PB. And basically, I kind of realized, after squinting at this one for a bit, that I could write this one with compose p as well. It's not quite as simple. I pass in f as my first parameter here. The identity is the second one. And let's just check that still type checks, and there we go. So basically, once I have compose, I get join, I get bind. So I can, at this point, in theory, define my my monad instance. So if I just take this, I've flipped across to this one for a reason I will explain in a moment, depending on whether anybody still has the will to live. So basically, to define a monad instance, so this is kind of when we say to the Haskell compiler that, yeah, we want you to type check and say that you've got all of the interface elements in this, then effectively, well, this is the identity, and this guy, well, he's just that bind we've just written. It should be. That serves me right for flipping too quickly. I'm trying to keep talking at the same time. It's like patting your head and rubbing your stomach. Okay, so if I just... Yeah, so that compiles. So there you go. We've gone from the twinkling in the eye of wanting to be able to divide by 0 to adding in this structure that kind of says we've got the arrows, we defined our composition, we defined our identity. We could then, in terms of those, and this code is basically the same, it's the same for all 4 of them. We can define our things. I'll post the code up later, and I'll give you a word of warning here, because I think I'm getting to a point where I've overstayed my welcome. With this one here, because I use type synonyms, you end up, it complains. I didn't understand what the compiler option did, so you can go through and effectively wrap it in all these, and the code isn't massively different, and the same is true here. You end up wrapping them. But it does work. So at this point, I'm going to flip back to here and say Kleisli category. So yeah, monads. So using that Kleisli composition, we go all the way to monads. So basically, is it really? Well, if you go look up the definition of monads, you'll find lots of stuff that talks about functors and natural transformations, e through mu, and you've got to prove that, prove properties about them, and then you've got to prove the monad laws. So, but as I said, Kleisli pointed out that if you define your structure in terms of basically a domain plus a sort of special range, and you put composition in there, you will get all those properties that you want from a monad. So this is me trying to draw a diagram to explain it. Effectively, let me see here. Yeah, we want to define this. So we start with A and B and a function between them. We get error A and error B. We want to make sure that we've got this. We can effectively do this by composing this identity function, which is the plain old vanilla identity function, along with one of those things that's on the screen. I can't remember which one, but it works, trust me. The natural transformations down to error are just those identities that we defined, so they're simple. And finally, you've got to define this mu thing, which basically takes your error squared and down to error. This is the join thing. So this is, again, me trying to draw a diagram to explain it. So we have error up here, error and A, and the equivalent in the error category here is, actually that's not the right term, but the equivalent down here is error A, and the equivalent here of A is error A. That is just the plain identity function. That again is the identity function. And then using Kleisli composition, so this is the same pattern that we saw before, we can effectively define the natural transformation mu out of that. And that, if you remember rightly, is that compose error ID that we saw in the code. So, and this is me drawing the diagram that goes the other way. So the executive computer programmers use things that look a bit like functions. They have domains and ranges, and it doesn't look like they're going to compose, and they don't compose in the ordinary way. They compose in this special way, and that these categories give you a nice way to describe and solve practical problems. So this is where we kind of move on to a slightly philosophical thing, and I'm not sure I'm doing Chris's blog post real justice. So realistically, it's going to be go back to the post and read it. But the key point for me that he was making was that programming languages in the past had their Kleisli arrows, the way that they dealt with all of these things, hard-coded, baked into the language. And that was all right, Structured error handling got added. Object-oriented languages added ways of dealing with global variables and passing them around. But as soon as you want to start dealing with things like, purity, parallelism, then suddenly you want to find you've got this problem here. You want more than one type of Kleisli arrow in the same language. You've hard-coded it in. Either you're going to have to hope that whoever defined them got it just right, or you can define them yourself. And that is where I ran out of steam with the slides. So there should be a question thing here saying questions, but done. I'm finished. So.